In the last class, we continued the discussion on transmission lines, and we moved from the telegrapher's equations into the solution for voltage and current on the transmission line. And from there, we made some very interesting observations. We said that if there's a transmission line, where the source is trying to send some wave to the load, and the direction of sending the wave is the positive x direction. So we said that in fact in steady state there are two waves which exist. One is the forward wave, the other is the backward wave. The backward wave is also called as the reflected wave, because once the forward wave hits the load, a part of it is sent back. So we proved that indeed, as a function of time, these two waves move along the plus x and minus x directions respectively for the forward and the backward waves. We proved this. Thereafter, we went back to the assumption that yes, we know that as a function of time, the voltage changes in a sinusoidal function. So we went back to the notion of freezing time and checking the variation of voltage only as a function of x. So to reiterate those results, we got something of this kind. So essentially the first term of voltage and current, having the e raised to minus gamma x term, corresponds to the wave which is traveling towards the load, or what we call as the forward wave, and the second term, which is the e raised to plus gamma x term, corresponds to the backward wave. In the last class, we proved two relations. We saw that essentially V plus by I plus is nothing but Z0, and V minus by I minus is nothing but minus Z0. So this is very important. This may look very innocent, but it has a lot of meaning behind this expression. We know that Z0 is nothing but the characteristic impedance. And we had defined it in this format, where R, L, G, C are per unit length quantities of the line. So these, if you keep omega constant, the fact that R, L, G and C correspond to some kind of impedance shows that this impedance depends on some of the characteristic properties of the line, that is the R, L, G, C. Hence Z0 is called as the characteristic impedance. Now let's suppose the line has only the forward wave. Only the forward wave exists and it is traveling towards the load but has not yet reached the load. This is very important. Suppose we have only the forward wave which is traveling, but it has not yet reached the load. So therefore there can be no reflected wave. in that case I can say that v of x is nothing but v plus e raised to minus gamma x, and ix is I plus e raised to minus gamma x, since reflected wave is caused only if the forward wave hits the load. So in that case, I can say that z of x, which I am defining as the ratio of voltage and current. So if voltage and current, that is v of x and I of x, denote the voltage and current respectively at any point on the line x, then z of x denotes the impedance, the effective impedance at any point on the line. So this is nothing but the effective impedance at any point on the line x. Fair enough, because v of x and I of x indicate the voltage and current at any point on the line. So if you substitute this over here, the two expressions, z of x essentially becomes v plus by I plus. And we have already proved that this ratio is nothing but z0. So we can say one thing. If a wave is traveling towards the load but has not yet reached the load, then the impedance that is seen at any point on the line is equal to z0. Now, as I said, this statement which I just made is instrumental in defining what is characteristic impedance or z0. So I can say z0, or the characteristic impedance, is the impedance seen by a wave which has not yet reached the load. Characteristic impedance is that impedance which is seen by a wave that has not yet reached the load. So that is like saying, if this is the starting point of the wave and it's traveling this way, it does not know what is connected at the load end. It could be any damn thing. But as long as this wave is somewhere in the middle and has not reached the end, irrespective of what the load is, it will always see the characteristic impedance of the line as the effective impedance. If you may recall that when we were discussing about characteristic impedance, this expression, I had mentioned that the characteristic impedance or Z0 is not a single impedance. You cannot call it as a single component like a resistor or a capacitor. ZL is a single component, yes. ZL I can draw this way. But Z0 I can never ever draw it as a single impedance like this, because it exists as a distributed function on the line. If this is the plus x-axis, at every point on the line we can say Z0 exists, because Z0 depends on RLGC, which are distributed quantities. They are not lump quantities. So don't make the mistake of thinking that if you open a line, you will see actually some impedance inside it, that is Z0. No, it never happens. Z0 exists because of the distributed quantities on the line. But it has some far-reaching applications, yes. But you cannot see it. So Having said that, let us rewrite the voltage and current expressions as a function of x. I'm eliminating the I plus and I minus terms and simply having these two expressions in terms of V. Now, let us change our perspective a bit. So far we had been talking about the source, the line, the characteristic impedance and how to define it, where does it exist. We have not talked much about the load. All we know about the load is that once a wave hits the load, the backward wave or the reflected wave is generated. So now we are going to see as we move along this course that the load plays an extremely important role in any transmission line problem. So therefore, let us shift our perspectives a bit. Let's call this load impedance as Z suffix L. And somewhere inside the line, let us write Z0. Z0 exists, as I said, in a distributed manner. So I cannot say that Z0 is at this point or this point. So many people say God exists everywhere. So Z0 is like that God. It exists everywhere on the line. So we cannot specifically say that, okay, only at this point it exists. No. So we had said that this is the positive x-axis moving towards the right. And we had said that let this point be x equal to 0. Let the source be at the origin. So what happens is, since the load is very important, as we are going to soon find out, let us shift the origin a little bit. Let us shift the origin from the source to the load. So let us define a new quantity called as L, or what we call as the length. Let us say L is equal to 0 indicates the load point, and moving towards the source indicates plus L. So in some sense we can say that shifting the origin from source to the load indicates that L is nothing but minus x. Supposing I am not putting any bound on the dimension of the line, I can just say by looking at the arrows which I have put for plus x and plus L, I can simply say that L is minus x. So we can now write the voltage and current as a function of L rather than x. Please note, it is nothing wrong if you use x. It is just that you will see from our analysis perspective that the load impedance plays a rather important role. looking at the application perspective, many a time, or rather most of the time, you will see that the source is fixed. The properties of the source are pretty well known. It is the load which creates most of the problems. So therefore, in the intuitive sense, it makes a lot of meaning to shift our focus on the origin of the problem to the load. Then again, you can easily solve all problems of transmission lines using X also. There is nothing wrong with that. However, the life becomes little more simple if you look at it from the perspective of the load, that is the L axis rather than the X axis. So using this, I can write V of L and I of L. So this would become V plus e raised to gamma L plus V minus e raised to minus gamma L. And I plus will become V plus by Z0 e raised to gamma L minus V minus by Z0 e raised to minus gamma L. So these are the solutions for the voltage and current on the transmission line, but using the L axis. So let us look at this voltage equation. Now, we have already proved that this first term indicates the forward wave, and this indicates the backward or the reflected wave. Now, in an ideal scenario, we would like that whatever is the wave that is generated by the source, or whatever is the energy carried by the wave that is coming out of the source, all the energy must go to the load. Nothing should be wasted. So therefore, a reflected wave is an indication of wasted energy. So in some sense, we can say that reflection, although it's a very interesting phenomenon, is not something very good as far as transmission of energy is concerned. So therefore, we would like that the reflected wave should be as small as possible. So to denote what is the strength, or how much of the reflection has actually happened, we define a quantity called as reflection coefficient. The symbol is capital gamma. Remember, small gamma was propagation constant, capital gamma is reflection coefficient. Now this reflection coefficient is also a function of the length L, which is nothing but reflected voltage at L divided by forward voltage at L. So we know what these are. It is simply the ratio of these two terms. So you can see that by taking the ratio, the expression becomes something like e raised to minus 2 gamma L. So in general, this is what we call as the reflection coefficient at any point on the line. Now, we have proved that gamma of L is nothing but this expression. Let us put L equal to 0. What is the speciality of L equal to 0? This L equal to 0 indicates the load, position of the load. So therefore, gamma of 0, that is gamma at L equal to 0, if you substitute L in this expression, this exponential term becomes 1 and all that you have is V minus by V plus. So therefore, this quantity where gamma at the load becomes a ratio of the magnitudes or the amplitudes only of the backward and the forward waves. I'll not say amplitudes, these are the core amplitudes or the amplitudes with which it would have happened had there been no attenuation. Because if you see gamma, that is the small gamma, which is a function of alpha and beta, out of that alpha is the quantity, as we have seen last time, that along the length of the line it determines how much the voltage changes. So if you look at V plus is the original amplitude with which the wave left the source, and V minus is the original amplitude of the wave when the wave leaves the load. So in general what happens? This is the way. This is how the wave flows. Now if this is plus x and this is plus L, the forward wave moves like this. I'm just going to draw the amplitude. So it essentially reduces exponentially with alpha. This is the forward wave. Let me also draw the reverse wave. The reverse wave will reduce exponentially this way. This is the reverse wave. So this amplitude, initial amplitude is V plus, this initial amplitude is V minus. So this is the way with which we can say that these two are nothing but the initial amplitudes when they are leaving the source and load respectively. So this is denoted as gamma suffix capital L, which is called as the load reflection coefficient or the reflection coefficient that is measured at the load. So you can see in general the gamma will change as a function of length because the magnitudes are changing. So in general, gamma, that is small gamma or the propagation constant, is a complex number. So therefore the reflection coefficient gamma is also a complex number in general. So we can write, since gamma is a complex quantity, capital gamma is also complex in general. Let me just redraw this properly. Yeah. So I hope this is clear. So in general, we can write that the reflection coefficient at any point on the line is nothing but the load reflection coefficient times e raised to minus 2 gamma L. This is very important. Now, let us again define impedance at any point on the line, that is ZL. This is steady state impedance. And by that term, I mean that both waves may be existing, both forward as well as backward wave. So Z of L is nothing but the ratio of voltage and current V of L by I of L So if you simply take the ratio, you will get this. So now if I put Z of 0, that is the impedance when L equals 0. What is that? What is the impedance at L equal to 0? It is nothing but the load impedance, because we have defined that L equal to 0 is nothing but the load. So this is ZL. So if you substitute that over here, these two exponential terms will become 1. This gamma suffix L, as I said before, it stands for the load reflection coefficient. So if you interchange the terms, gamma suffix L comes out to be this: ZL minus Z0 by ZL plus Z0. So this is the expression for the load reflection coefficient in terms of the impedances. Now let us see some very interesting properties over here. So what did I say about reflection? Reflection is something that we don't want. It is a very undesirable phenomena which indicates that the line is not 100% efficient and all the energy is not being transferred to the load. So therefore, ideally, this reflection coefficient should be 0. So we can say the first result is that gamma L will be 0 when ZL is equal to Z0. When the load impedance is exactly equal to the characteristic impedance. In that case, all the energy of the forward wave gets absorbed by the load and there is no reflected wave. This behaves like a perfectly opaque object which absorbs all the light. So this case is called as a matched condition. And this matched condition is highly desirable. So most transmission line engineers spend their efforts trying to achieve this. So now let's look at result 2. What can be the maximum magnitude of the gamma L? So if I say gamma L is ZL minus Z0 by ZL plus Z0. What is the maximum value of this magnitude of gamma L? What do you think it is? If you look at this expression, you will see that the maximum value of mod gamma L will be 1. The reflection coefficient can never exceed 1, and that makes a lot of sense also. When a wave hits a mirror, the maximum amount of the wave that can come back is itself. The load is not an amplifier. It cannot amplify the incident wave. So say for example, if you stand in front of a mirror, you will see your own reflection. You will not see more brightness in your reflection. That's just a small, crude example. This indicates, what does it indicate? Maximum reflection, which is undesirable. But just by telling it undesirable, we cannot run away from it. We need to see under what conditions can this gamma L become 1. So this happens under 3 conditions. The first condition is when ZL is equal to 0. That means the load impedance is 0 ohms. And this is what we call as a short circuit. So short circuit is not just bad from electrical safety standards, but it can also cause reflections in transmission lines. The second case, when mod gamma L can tend to 1, is when ZL tends to infinity. And this is what we call as an open circuit. What about the third? In which other condition or which other value of the load? Now, why I am considering values of load only? Because that is something which is in the control of the engineer. Because once the line is made, you cannot change Z0. Once the transmission line is made, you cannot change Z0. So, looking at this expression for gamma L, under what other condition can mod gamma L tend to 1? And the answer is when ZL is purely reactive or imaginary. That means when load is inductance or capacitance purely. And that makes sense also, because as you know, L and C are reactive elements and they cannot dissipate power. So therefore they will reflect back everything, just like open or short circuit. In case of open circuit, current is 0. In case of short circuit, voltage is 0. So therefore they cannot dissipate power, these kind of loads. So therefore it has no option. So therefore, as per the principle of conservation of energy, if the load is not dissipating any energy, all of it will be reflected back. And this is what happens. So, now we can also say that if we know the load reflection coefficient, we can also find out the reflection coefficient at any other point L, because we know that gamma of L can be found out using this formula. So once we know the load reflection coefficient, we know gamma, and we all we need to do is simply put the value of small l, and we can get whatever is the gamma we want at that particular position L. So now let's come back to the expression for Z of L, that is impedance at any position on the line. So this, as we proved, is nothing but Z0 times Now you already know the expression for gamma L, That's load reflection coefficient, which is nothing but ZL minus Z0 by ZL plus Z0. So if you substitute that, this is what you will get. This is cos hyperbolic. These are hyperbolic cos and sine functions. Now what this means is, if you know the load impedance and you know the characteristic impedance and you know the gamma, which is a line property, you can find out the impedance ZL at any point of the line using this relation. This relation is called as the impedance transformation relationship. Why do we call it transformation? Because in this transmission line arrangement, when L is equal to 0, the impedance is ZL. But at any given point L, the impedance is a function of ZL as well as Z0. So with length, the impedance is also changing. Now this is a very interesting phenomenon which you don't get to observe. Just because the impedance at the load is ZL, it does not mean that the impedance at each and every point is also ZL. The impedance at any point on the line changes as a function of ZL, Z0 as well as the length or the distance from the load, and this is positive L. Now this is in general the case for any line having a propagation constant small gamma. Now we had said that this propagation constant small gamma is nothing but alpha plus j beta. We had said that out of alpha and beta, the villain is alpha, because that causes the wave to attenuate as it travels along the line. So therefore we had said that we would ideally like a line to not cause any attenuation, and such kind of lines are called as lossless lines. When alpha becomes 0, that means the propagation constant gamma is equal to j beta. Can beta be equal to 0? Think about it. You should be able to answer this question looking at the discussion in the previous class. So alpha equal to 0 is definitely possible. In real life also, as I mentioned in the previous class, technology has advanced and we can get lines these days with alpha nearly equal to 0. So therefore, for a lossless transmission line, the impedance at any point on the line ZL becomes, simply substitute gamma as j beta, and this is what you will get. So the cos hyperbolic will become cos and the sine hyperbolic will become j sine. I can also write, if I divide both numerator and denominator by cos, I can write this. This is the impedance transformation relationship for lossless lines. So now, from this point onwards, let us make our life simple. Let us assume that all the lines that we have are lossless unless we explicitly mention otherwise. And that is a fair assumption also. Now, if you look at this impedance transformation relation, as I said earlier, if you know the impedance at any point on the line, you can easily calculate the impedance at any other point on the line also. So that's just the way it is. So this is a very important relation. So for lossless line, which two quantities out of RLGC should be 0? R and G should be 0. Why? Because each of the lines should be a perfect conductor and the medium between the two lines should be a perfect insulator. This makes R equal to 0 and G equal to 0. That means the line can neither attenuate on the conductor, neither can it attenuate inside the medium between the two lines. So therefore, we know that the propagation constant gamma, which is defined in this following manner, this is nothing but, for lossless line, both R and G become 0. So this is what you get. So this is nothing but J beta. So the propagation constant beta for a lossless line is nothing but omega under root LC. In the last class, we had also defined beta as 2 pi by lambda, and omega we can write as 2 pi f LC, which is nothing but 2 pi by lambda. So I can cancel the 2 pi and 2 pi, and I can say f lambda is 1 by root LC. What is f lambda? Frequency times lambda is nothing but the wave velocity. So you can easily find out what is the velocity of the wave inside the transmission line if you know the per unit length inductance and per unit length capacitance. So this is a very important relation. Now, this wave velocity is also called as phase velocity. We shall understand the meaning of this word phase velocity later. a lossless line, the characteristic impedance Z0, is so if R and G both become 0, this is nothing but under root L by C. So what can we say about Z0? We can say for a lossless line, Z0 is always real. This reminds me of one small change which I forgot to mention. In the third condition, for mod gamma L equal to 1, the assumption is if Z0 is real. This is for the third condition. So this is a very important result. We have proved that if the line is lossless, its characteristic impedance will always be real. So this is the way you can be sure when you go to the market to buy a transmission line. If somebody is trying to sell you a transmission line which has a complex impedance, you will know then and there that it is a lossy line, because a lossless line always has real characteristic impedance. Now let's ask the alternate question. If somebody gives you a line and says that its characteristic impedance is real, does it always mean that the line is lossless? Now I am asking the converse question. We have proved that lossless definitely means that the Z0 will be real. But given that Z0 is real, will it mean that the line is lossless? Think about it. So, having said that, let us define a quantity called as normalized impedance. Now, normalized impedance is a dimensionless quantity where we express any impedance with respect to the characteristic impedance, because characteristic impedance exists throughout the line, not at a single point. So therefore, we define every impedance with respect to characteristic impedance. So this is defined as absolute impedance divided by characteristic impedance, which is Z0. So let us say for any point on the line having impedance Z of L, I can define the normalized impedance, which is defined as small z of L. This is nothing but capital Z of L divided by Z0. So in this case, the impedance transformation relation using normalized impedances becomes small z of L is equal to small zl. Now this is the normalized load impedance, where small zl is equal to capital ZL by Z0. plus j tan beta L divided by 1 plus j small zl tan beta L. So now there is a lot of benefit on using normalized impedance, because one of the first advantages, we are essentially doing away with the extra variable, that is Z0. We are expressing the impedance as a consolidated function of any impedance Z and Z0. So now let's investigate something. Let's say that at any, or not any, at a point L is equal to L1, the normalized impedance is Z1. Then what will be the normalized impedance at L2, which is L1 plus lambda by 4, where lambda is the wavelength of the wave? How will you do this? I can say that Z of L2 is nothing but the load impedance ZL. I am just using this relation, J tan beta L2 instead of doing this, let me first write Z1 properly. So I can say Z1 is nothing but beta L1 divided by 1 plus JZL and beta L1. This is using the relation. So Z2 is nothing but ZL plus J tan beta L2 divided by 1 plus JZL tan beta L2. So we can write this as ZL plus J tan beta. I can substitute now. L2 is equal to L1 plus lambda by 4. How would this be? So what is beta lambda by 4? Beta, as you know, is 2 pi by lambda. This is lambda by 4. So this is pi by 2. All you need to know is your trigonometric identity. Of tan of pi by 2 plus theta, which is nothing but minus cot. So this is what it becomes. So if I now write this using a tan function, I can very easily prove that this is nothing but 1 plus jzl tan beta L1 divided by zl plus j tan beta L1. If you look at this expression versus Z1, you will see that they are nothing. So what have we proved? We have proved that Z2 is nothing but 1 by Z1. Now what is the peculiar thing about Z1 and Z2? These two impedances are at 2 points on the line which are separated by a distance of lambda by 4. Let's say the load is somewhere here. Let's say this is L1 and this is L2. The distance is lambda by 4. So the impedance at this point is Z1 and this is Z2, and this is normalized impedance. So we have proved that as you move by quarter wavelength or lambda by 4 any direction on the line, the normalized impedance will invert itself. Please remember, absolute impedance will not invert because it has a unit ohm. Inversion of normal impedance would mean mho. So we have proved that as you move along a distance lambda by 4, not the actual impedance but the normalized impedance inverts itself after moving lambda by 4. So let us quickly summarize what we have done today. So today we continued the discussion from the solution of voltage and current on the line. So we discussed the definition of characteristic impedance, which is nothing but the impedance seen by the forward going wave until the time it has not reached the end or the load. This is how you define the characteristic impedance. So then what we saw is that we said that let us have a change in the origin. Rather than making the source as our origin, we shall make the load as our origin. So therefore there was a slight change. We moved from the x-axis to the l-axis, where the positive L is nothing but moving from the left of the load, or away from the load. We defined something called as reflection coefficient. Then we talked about something called as load reflection coefficient, and we also said that if you know the load reflection coefficient and you know the properties of the line, you can find out the reflection coefficient at any other point on the line. Then we said under what condition can the load reflection coefficient be made 0. That is very desirable condition, or what we call as the match condition. Then we discussed the worst case, when the load reflection coefficient can become 1. These are the conditions. After that, we proved that if you know the impedance at any point on the line and you know the characteristic impedance, you can find out the impedance at any other point using something called as the impedance transformation relation. And then we sort of made our life simple by saying that let us consider all lines to be lossless unless mentioned otherwise, because that is a very valid assumption, because most lines today that are available in the market are lossless. So our analysis became a little more easy. We found out what is phase constant, we found out what is velocity of the wave for a lossless line, and we also saw that for a lossless line the Z0 is always real. And we finally proved that as you move by a distance of lambda by 4, the normalized impedance, which is a unitless quantity, inverts itself. So we shall continue from this point on in the next class.